the handout that I just gave you, two of them, the big one with just the one slide on it, that is something that you guys hopefully keep, learn. We're going to use it all the time, so it's going to be something that I try to train you to just be kind of instinctual on. But if you want to use it on tests and quizzes, by all means, bring that to class. You can use it on tests and quizzes. Okay. The other one, we're going to do some proofs here today, and the idea with proofs is they're structured to them. You see there's like a chart on all of them. I don't want to spend a whole lot of time writing that chart down and wasting class time that we could be used to be discussing the contents of what's in that chart. So as we do proofs, it won't always be this way, but as we do proofs, I'm going to try my hardest to print them out for you, okay? There might be times where I make you write them down, but for the most part, I'll try to print them out. Now, I'm also, and I've struggled with this for years, is kind of stuck on, do I print off, if we're going to do 10 proofs in a period, do I print off one slide pages and give everybody 10 pages of paper, so I waste 400 pages of paper in a day? Or do I print 4 on a page and you can't really see them very well or write on them very well? Okay? So I'm kind of stuck in the middle on what I do, but I'm probably going to try to save paper and present them that way to you, and then you kind of adjust with the way you write. Might have to maybe adjust the way you take your notes with them, but I think it's going to save you a little bit of time in regards to writing stuff, save a little bit of effort. So that's kind of the plan as we move on. When we go over proofs, guys, there are going to be things that you're going to be thinking, well, he spent just 40 minutes talking about 2 questions. That might happen. There might be times where we spend 40 minutes talking about just 1 question, okay, 1 proof. If we devote that much time in class to something, to one thing, that's probably a pretty important thing, right? So I want you, as we're working with proofs, write down everything, okay? In a way that I try to motivate people to do that is occasionally, I'm not going to say it's going to happen 1 time or 2 times or 3 times. I don't know how many times it'll happen. But you might come for a pop quiz and I say, hey, quiz today, but go ahead and use any written notes that you have, okay? And if you don't have written notes, you're kind of in a bad situation compared to everybody else, right? Does that make sense? So I want you to write these things down, make sure you're following along. And just what we write down might not be everything that you need to write down to make sense of what's going on with these proofs. You might have to write little explanations for each statement on why we wrote them that way, okay? So be very detailed in your notes as we do these, okay? I think yesterday we got to this, but we're kind of running out of time, so I want to reiterate what a proof is. A proof is a mathematical statement. It's a convincing argument that uses what we call deductive reasoning. So we talk about that. That's using previous known facts, okay, to come to a conclusion, to say why I know something exists the way it does based on the way previous ideas exist, previous statements being true, okay? That last bullet, I think, is pretty important for what we're going to be doing. It says, if I have statement D, so it's the 4th statement that we've made. The only way that I know statement D is true is because I'm able to decipher and determine that statements A, B, and C were true, and D followed logically from those 3 things, okay? But if any of A, B, and C were false, then I can't make the statement that D is true. Does that make sense? Okay? So that's what a proof is. If we look through that handout that has the 4 slides on it, there are some charts there that have like 6 or 7 steps on them. Each one of those steps will be somehow determined to be true, but the ones that follow after each step are only true because of the ones that came before it were true. Okay? So that's something we got to keep in mind. Every proof we do, every proof that we come across will look like this. Okay? It's called 2-column proof. Okay? What I kind of explain this as to every class is kind of something that you're used to doing in an English class. If I I was your English teacher, or Miss Ellington's your English teacher, and she says, hey, we got a paper due in 3 weeks about whatever topic, but this week your blank is due about that topic. What would be the first thing that you do in writing a long paper? Okay, maybe we got like a 10-page research paper or essay that we've got to do. What would you do first in an English class? You'd write a what? Say again? Okay, so that's going to be part of your introduction, your body, your conclusion, all that kind of stuff. That's going to be the structure of your final paper. But in preparation, before I even start writing my paper, what would you do? Okay, you'd figure out what your topic is, but then how are you going to structure your arguments towards that topic? You're going to create a... Okay, what do you do before a rough draft, though? You brainstorm, but what's between brainstorm and rough draft? Starts with an O. Okay, you're going to organize things in a... Who said it? Outline. Okay, you can make an outline, right? Okay, you guys have done that before? Hunter, made an outline before? Okay. Then you take your outline and you actually take the information, your key points in your outline, and you compose it with a body, an introduction, a conclusion, in pro-style writing, right? And you create your argument. Okay. Our proofs are kind of the combination of an outline and a rough draft. Okay. A true mathematical proof. Like if I was a career mathematician, okay, and I'm doing research or something like that, and I come up with this proof of something, and I'm going to publish that, I'm not going to publish it like these things in front of us. We're going to publish it in pro-style writing. We're going to publish it as a paragraph paper type thing. Does that make sense? So we're going to conduct the outline rough draft. And then once we get good at doing that with proofs, I'll show you how you then take your rough draft or your outline and write it in paragraph form, which is actually pretty easy. But right now, what we're going to do is kind of rough draft outline type things. In regards to that, when you do an outline, you do a rough draft, does everything in your outline and rough draft end up in your final? No. Sometimes you cut things out. Sometimes you refine things a little bit, add them a little bit, adjust them a little bit, right? But for the most part, your rough draft and outline should model your end result, correct? Okay? Same thing here. We might, when we want to write our final draft, we might have to cut something out. Maybe something didn't make a whole lot of sense or wasn't needed, so we remove it. Okay? So those are things that we'll talk about as we move on through the year. When we have a proof, there's always going to be some statement that we're trying to prove. Okay, so they'll start us off with that information, and it'll be something like this. It'll be, I'll say like, prove that if something, then something, and what do we recognize that structure looks like? We've been working on those types of statements, right? Been working on if-then statements, okay? The prove parts and the given part of our proof that we're going to work on, okay, this here ends up being your given, okay? So in an if-then statement, they ask you to prove a particular if-then statement. The hypothesis is what we call our given. That's the statement that we're going to agree on as being true so that we can start the problem. If we don't have anything that is true, we can't start the problem. Does that make sense? We need a foundation. So that's our given. This then is going to be our proof. So in this particular question, we're going to actually walk through this proof later on. It's one of those other slides on that handout. But the way this would be provided, it would say, if measure of angle 1 equals measure of angle 3, then measure of angle AEC equals the measure of angle DEB. They would ask us, prove if measure of angle 1 equals measure of angle 3, then measure of angle AEC equals measure of angle DEB. So it allows us to kind of take that if-then statement apart and decide which one of those statements, the if or the then, allows me to kind of get the ball rolling with this process. Okay? Once we identify the given and the proof, this statement right here, okay, will always be our given. Our first statement will always be given. So a lot of times they call these two-column proofs. You got obviously two columns. Sometimes they call them T-chart proofs. But your left column will be statements. Okay, those are facts that we know are existing for our particular problem. Okay, over here, these reasons would be why we know we can make those statements. And those reasons are going to be things like postulates. They're going to be definitions. They're going to be other theorems. And we'll talk about our first couple theorems in the next couple days. But you write a statement on the left-hand side, and then you tell us why that statement is true on the right-hand side. Then you go to the next statement on the left-hand side and tell us why that is true on the right-hand side. Okay? So a lot of those properties we talked about yesterday, the addition property, quality, the reflexive property, substitution, those are going to be some of our reasons. Okay? All our vocabulary words are going to be some of our reasons. Okay? Last class, we talked about this as we were doing a proof, but our reasons are going to be, if we think about our glossary and our textbook, so let's say we're at the end of the year and we're doing a proof. So we have then talked about 13 chapters worth of information. And let's just say that there's anywhere between 10 to 20 vocabulary words in every chapter. Some of there's more, some of there's less. But let's just say 15. So let's say there's about 200 vocabulary words that we have learned at the end of the year. Does that make sense? Okay. There's going to be about 30 postulates. And there's probably around 100 theorems. Okay. So if we do that math, there's about 330 to probably about maybe 400 different types of statements that we have to catalog and remember. Okay. And I took all these files out of my desk. These are my files for teaching roads, teaching BAP, teach policy, licenses, certificates, pay stubs, all that kind of stuff, okay? And it's a mess. It's a terrible organization, right? And if Landon asked me, Mr. Fay, can I see your teacher's license? I'd have to search this folder, go through all of it. Nope, not in there. Look at this one. That's going to be a time-consuming thing, right? To find my teaching license. But I have a terrible job. I do a terrible job of organizing that type of stuff, okay? Your brain operates the same way. Your brain is a filing cabinet of information, okay? But if your filing cabinet doesn't have any organization to it, when I ask you to find a definition and utilize a definition, it might be really hard for you to find it. Does that make sense? We've talked about midpoints. We've talked about vertical angles and angle bisectors, and you've mastered those things. Okay? But it's maybe been a week, 2 weeks, 3 weeks, 4 months since we used those, and it might be hard to go grab that. Does that make sense? Remember where you put it in your mind. My suggestion is as you're doing proofs, and you're going to find out once you start doing this, how beneficial it is. As we introduce a new vocabulary word, write it down on a flashcard. As we introduce a new theorem, write it down on a flashcard. Okay? And you create kind of this catalog of terms and statements that when you get to your homework and you're working on proofs, you can focus on what file to be using. Does that make sense? Okay? You can ask Mr. Moore how your brain kind of processes things and stores things and schemas and stuff like that. It's very much like a filing cabinet, okay? And if you don't organize it well enough, it's going to be hard to recall things and reuse things, okay? So that's just a pointer before we move on with these things. And that's what people struggle with, okay? And I'm searching out of 400 different statements which one to use. Maybe I can't remember what all 400 are, okay? So that's something we'll have to work on. Every proof will have a picture. Okay, everyone that we work on early on will have a picture. And now you see this one's got 5 statements and 5 reasons. There might be 12 statements in the next one, 12 reasons. There might be 7 in the next one, and 7 reasons, okay? There's no kind of limit to how many statements and reasons we'll have. We don't know that really until we start working on the problem. Okay? Now, proofs can be difficult, and I'm not going to read this through right now with you. We will target this when we start our first question here in a little bit. But these 7 steps will help you if you get stuck. Okay? Early on, I'm going to try to use these 7 steps every single time. And if you can do these first 5 steps, you'll get 80% of your proofs done and correct every single time. 6th and 7th step are using essentially the law of detachment and the law of syllogism that we talked about a couple days ago to create new facts. Okay, it's to kind of shed light on kind of the hidden information inside our proof. Okay, so steps 6 and 7 take a little bit of practice, take a little bit of creative thought to come up with. Okay, so we'll use that. Like I said, bring that to class. Every day we do proofs, tests and quizzes. You're more than welcome to have that out and use that as kind of a guideline. All right, so like I said, steps 5, 6, and 7 are going to be maybe problematic. 5 isn't too bad, but I want to make sure that we understand what 5 is saying. If we read step 5 in that handout, it says you're going to look at your picture. Does it deal with angles or segments? If angles, you will probably use the angle addition postulate. If segments, you will probably use segment addition postulate. Okay? Now that statement is just to start us off. Okay? In 3 or 4 weeks, we're going to add things to that. So it won't always just be segment addition and angle addition. What is really important about step 5 there is, in parentheses, says eventually, this will not always be the case, but we want to write down what we are able to verify by pictures. You remember last week, or remember 2 weeks ago, I said when you look at a picture, there's not a lot you can tell me. There's not a lot you can be confident in. Okay? I don't want to look at a picture and say, well, that looks like a right angle, until they tell me it's a right angle, correct? If I look at this up here and I look at A, B, and BC, those segments, do A, B, and BC look the same? Do they look equal? But that's something that we don't want to say until we are provided information that indeed AB is equal to BC. Okay? But there are a handful of things that we can tell. Okay? And just a little bit of practice at that. If I look at angle 1 and angle 2, what kind of angles are 1 and 2 there together as a pair? Angle 1 and angle 2, do they form anything together as a pair that might be useful to us? Great. Okay, so now what do you mean by supplementary? They're going to do what? Add up to 1A. So the argument here and you are 100% right. Okay? But we want to be careful on this because when we write a proof, we want to make sure that we don't lose anybody and we don't have any gaps in our proof. If I look at that picture, okay, would you guys all agree that those angles are going to be supplementary? They're going to add to 180, right? I'm going to ask you, why do you know that? Because that's what we want to do. If I'm in a courtroom and I say, Drake didn't commit this crime, the jury's going to ask me, well, why do you know that? So you got to have a defense. Why do I know 1 and 2 are going to add to 180? What kind of angles as a pair are they? They're a linear pair. Okay? So we can visually look at a picture and say they're a linear pair. They form that line AC, right? And we had a postulate that said linear pairs are supplementary, right? So we know 1 and 2 are a linear pair. That means now with this postulate that 1 and 2 are supplementary. And what's supplementary mean by definition? They add to 180, right? So you see by looking at that picture, people want to jump from 1 to 2, look at the picture, well, they're going to add to 180. But I want us to be able to explain why. Okay, that's what geometry is about. That's what this proof stuff is about. Not just going from step 1 all the way to a conclusion, but being able to explain why I go from step 1 to step 2 to step 3 and then step 4, my conclusion. Okay? So we want to be able to do that. We can look at things and say that they're a linear pair. Okay? Can I look at maybe I went too far. Can I look at these two and talk about what kind of angles those are? Those vertical? You guys remember that? Okay. So we're going to maybe talk about a relationship that we'll learn about vertical angles. What could I say based off the picture, based off the information that they give me, too far again, about that point right there? What kind of point is B? If I know that information right there, B is a midpoint of segment DE, right? Okay. Is it a midpoint of segment AC? It looks like it could be, right? But our eyes don't have the ability to tell me what AB's length is and what BC's length is, so I cannot make a definitive conclusion that that's a midpoint of AC. But I can, based off the notation, make a definitive conclusion that B is a midpoint of D to E, okay, but not of A to C. So there are things that we can gain from a picture, right? And once we write down steps 1, 2, 3, and 4 off of that worksheet, off that handout I gave you, step 5, there's usually 1 or 2 things that are going to be hidden or implied inside your picture that you got to kind of pull to the surface. Linear pairs are common. Vertical angles are common. Angle addition and segment addition early on will be the most common things that we're going to look at. And we'll see that in an example here in a little bit. But that's what that step 5 is kind of talking about. Okay? So I want to jump down to this slide here. I'm not sure which slide that is on your handout. I want to do this one because I think it has an algebra background to it, or its backbone is algebraic, which I think we're probably more comfortable with right now, especially with proofs. Did you guys ever do last year like stuff like this where I don't know if Miss Coles continued to do this stuff towards the end of her career, but we start with like an equation like 2x plus 3 minus 4x equals maybe 2 times 3x plus 1. And they would say if that is given, that's what we start with. Step 2, they would do something like this. And you have to decide what is the property that allowed me to take that thing and move them to there. And you would write, does anybody know that property? Commutative. And then this next step, you would do something like this. Have you guys ever done anything like this? Okay. So you did algebra, so that would be the associative property, right? Okay. And then you went ahead and you said, well, that becomes negative 2x plus 3 equals 2 times 3x plus 1. And maybe you say, well, that's combining like terms, or it's really the distributive property. And then you continue to go through. Maybe the next step you would distribute on the right-hand side, right? And then you would maybe move something to all my variables to the left-hand side. So use the addition property, subtraction property of equality. You guys remember doing those things? Those are algebraic proofs, okay? And the algebraic proofs, these reasons over here are telling me why it was legal to go from step 1 to step 2 and just move those terms around. What allows us to do that, okay? So these proofs, if you think about what you did last night in your homework, okay, your proofs are a collection of a bunch of those statements or homework questions that you got yesterday, okay? So we'll start with this one and see if we can kind of maybe recognize some similar relationships of what we did last year compared to last year. All right, so the first thing I want to do here is I want to write a statement that the textbook or maybe even the end of course exam would write to us or write for us, and all of this stuff would not be present. Okay, so that would not be here. All they would say to start the problem, they would write the words prove if C is the midpoint of AD, then X equals 6. That's what this textbook would start you with. That's what maybe what the end of course exam would start you with or could start you with. And then we are left to create everything else up there. Okay? Now, as we work through examples, guys, early on, you see most of the stuff is already filled in for us, right? Okay? We'll start to slowly delete some of that stuff, and eventually I will start you only with that red statement, and you got to come up with everything. Okay? But we'll build to that. I'm not going to start you off day one that way. I think that would be cruel or unusual. Okay? But what we do, if it says prove if C is the midpoint, the if part, your hypothesis is that right there. Your hypothesis, all you do is you cut and paste that, and it becomes your given. That's the information that we're going to start the proof with. Okay? We're all going to be under the assumption that that is a true statement, that that is happening in front of us for our particular problem. The then part becomes your proof. Okay? So the given is your hypothesis. The proof that we're trying to target is your conclusion. Okay? Once we have that stuff kind of deciphered and figured out, now, in this question, they would also somewhere maybe have to tell me that we've got that picture where AC is 4x and CD is 2x plus 12. But generally, that prove if C is the midpoint of AD, then X equals 6 would be enough for us to get the ball rolling with a proof. Okay? The first thing you do, look at that sheet I gave you. Step number 1 says write down the given statement. Okay? And reason number 1. Well, your given statement, that green statement is going to go right there every single time. And the reason we know that that is true, so this is the statement we're going to make, and these are the reasons, okay? Maybe the logic is why it's true. Well, this is true because it was provided for me. It was given to me by the author, and we're just going to start with that assumption. Okay? Does that make sense? To start building a proof, I at least have to have one fact that I know. Okay, and that's the one fact that they're going to tell me I know to be true. Okay. Step 2 says if there is information regarding equal and congruency signs. You're going to fill that into your picture. So I'm going to look in my given statement, and I'm going to look for the equal symbol, and we'll look for the congruent symbol. So I'm going to look for these two things. I'm going to look for either that or that, physically written in statement number 1. And you don't see any of those, right? So you can skip step 2. Gets us to step 3. This is where it starts to get a little bit more difficult. Because step 3 says look at your given, and if there are vocabulary words in your given, those words should tell you something about our specific problem. Okay? So vocabulary words hide facts to us. Okay? So what's the vocabulary word that we're seeing in our given? Midpoint, right? So then we have to think, okay, if midpoint's the vocabulary word, now I got to think about, well, what does a midpoint do? A midpoint takes a segment, an overall segment like segment AD, and it cuts it into 2 smaller congruent segments, doesn't it? Okay? So what we want to be able to do then for our specific case, for our segment AD and our point C, we want to develop a relationship that is determined by that vocabulary word. Would you guys agree that if C is the midpoint here of A to D, then AC, that segment, would be the same length as CD. And that's what they write right there. Okay? So the midpoint vocabulary word produced statement number 2. Okay? If we think about, if I were to look in the glossary of my textbook and look up midpoint, it's going to say it is a point that takes a segment and divides it into 2 congruent segments. But we have 2 congruent segments right there. They're just specific to our problem. Does that make sense? Now, how did I know that AC was congruent to CD? It's because we knew what a midpoint was, right? So our reason over here will be the definition of a midpoint. Whenever I use a vocabulary word to create a statement, my reason for creating that statement is because I knew what the definition of the vocabulary word was, right? Okay? So AC is congruent to CD is only true because that's what the definition of midpoint lays out for me. Okay? Now, the next statement is kind of a procedural thing. Okay? But I think it makes sense to talk about this way. If I want to start doing some algebra, because we start with the midpoint and then we get down to x equals 6. So I know I've got to do some equation stuff here. Well, I can only add numbers. I can only do operations. Add, subtract, multiply, and divide with numbers, right? Or with symbols that represent numbers. So I can't add, subtract. Think about this. I want to give you 2 shapes and ask you to divide a circle by a square. Can you do that? That makes absolutely no sense, right? Okay? So I can't add these segments. Even when we do segment addition, guys, we're really not adding the segments. We're adding the segments' lengths, right? So what we want to do is, right here is telling me we have 2 segments that overlap each other, 2 segments that would be cut and paste and land on top of each other. Right here, we need a transition to say, whatever that segment is, the number that characterizes it, its length, is equal to that segment, whatever it is, its length. Does that make sense? And that's kind of a procedural thing. You're going to do that over and over again, and you'll get used to it. But if I want to start doing algebra, I can only do algebra with measurements. I can only do algebra with distances, okay, or angle degrees. I can't do it with shapes. So I need to make this statement. And the statement is, the back of our book is going to call it this, okay, or most of the time Math Excel is going to call it that. If you want to call it the definition of congruency, okay, that is fine as well. If I were to look up congruency in the textbook, I actually have to look up congruent segments in the textbook. The definition will say there are segments that have equal length. Okay? And that, like I said, that step 2 to 3 is kind of a procedural thing that you'll get used to. So now we've done our vocabulary. Step 4 says, from what you learned in your vocabulary, go to your picture and draw that in. So our vocabulary told us we had 2 segments congruent, right? AC and CD. So I've already drawn that in my picture. Okay, you'll find out that step 4 is pretty important more in chapter 4 than it is in chapter 2. Number 5 says, look at your picture now. Does it deal with angles or segments? And ours deals with segments, right? So we want to use some type of maybe segment addition concept. Okay? Well, right now, do we know that AC is equal to CD? So this is a number, right? CD is a number. Well, those 2 numbers are equal. When I know what X is, isn't X a number? So then 4X would be a number, right? So would you guys agree that 4X is an alternative way of talking about the number AC? That make sense? It's like if I say Mr. Lindsay, that's a different way of talking about Drake, correct? Okay? So whenever I see Mr. Lindsay, I can replace it with Drake. Or whenever I see Drake, I can replace it with Mr. Lindsay, right? Well, if I see 4X, can't I replace that with AC? Or where I see AC, can I replace that with 4X? Does that make sense to everybody? So what I want you to recognize here is that steps 3 and 4 are the exact same thing. Step 3 and step 4 are identical steps. But wherever I saw AC, I replaced it with what it was equal to, 4X. Wherever I saw CD, I replaced it with what it was equal to, 2X plus 12. Does that make sense? When I replace things like that with what they're equal to. You guys remember what property that is from yesterday? Substitution. Good. Okay. So we have the substitution property here. Just spell it right. Substitute. Okay. Now, the next statement is hidden for us. The next statement we got to figure out. But look at the reason they gave you. The reason says they subtracted, or they used the subtraction property equality, which means they removed something from both sides, right? What would you, if you're looking at step 4, what would you remove from both sides? Most people would take that 2x away, right? So if I remove that from both sides, I'd be left with 2x equals 12. So that's the subtraction property equality. So now steps 4 and 5 and 6, those kind of align well with what maybe some of you said you did last year in algebra. We did this stuff over here, right? Okay? Being able to talk about why we're doing certain algebraic steps. So if you got 2x equals 12, what are you going to do next to get x equals 6? You divide. Division property equality. So divided by 2. Some of you might say, I use multiplication property equality, but then you would have multiplied by 1/2, right? Those are both feasible answers, logically saying why I can go from 12x, or 2x equals 12 to x equals 6. Okay? There will be times where there might be 2 or 3 different reasons, or 2 or 3 valid pieces of information or statements, or reasons, I guess, that back up a statement. Okay? All right, so let's come up to this one. Okay, and kind of address. So this is fully geometric. Okay, 100% geometric. No like algebraic substitutions. And now we do start doing some algebra, but there's no substitutions like 4x and 2x plus 12 and that kind of stuff. Okay. Here it says, so basically this is the one that was started with this slide here. Okay. So they might have started us with the prove if measure of angle 1 equals measure of angle 3, then measure of angle AEC equals measure of angle DEB. So that's already set up for us, so I don't want to talk about that again. But the first thing that we always write down is our given. So they write down our given right here, number 1, and our reason will be given. Okay, that should be easy points. Now let's kind of talk before we start maybe messing through this problem. Let's talk about what they're doing here. They're saying if I look at 1 is equal to 3, can we then prove that that angle right there, that blue angle, is going to be, I don't know how this color is going to work, okay, is going to be the same as that purple one, or pink one, whatever color that is. Well, think about this. What do you know about angle 1 and angle 3 at the onset? They're the same, right? Give me a number. Any number you want. I heard somebody say 13. Okay? Maybe it was one of you, maybe it was a voice in my head. So 13 degrees. Give me another number. Okay, so 13, so those are 13 degrees right there. Let's say this angle here where they're overlapping is 6. Wouldn't the blue angle be 13 plus 6, which is 19? Wouldn't the pink one be 13 plus 6, which is 19? And isn't that blue one AEC? And isn't the pink one DEB, the things that we wanted to prove? Does that make sense to everybody? So, specifically, we just proved that this should be true if I chose the numbers 13 and 6. Okay? But we want to show that this is always true, no matter what you choose for those numbers. So in order to show this is always true, I have to go through this. I go, well, let's do it with 14 and 6. And we get 20 and 20. And then I say, okay, 15 and 6, I get 21 and 21. And then I say 16 and 6, I get 22 and 22. And I have to go through all my numbers to do that with whatever in 6. And then I got to go back and say, okay, now let's change that 6 to 7 and do the same thing. And then say, okay, once we do that, go back, change that 6 to 8 and do the same thing. And then go back and say, okay, once I get all those done, now I go back and say 6 is 6.01. And then 6 is 6.001. Can you see that would be an infinite number of things I have to prove, and I can't do that? Okay? So when we want to do these proofs, we use arbitrary values. We use symbols that represent those infinite number of options for 13 and 6. So when I say measure of angle 1 equals measure of angle 3, right here, understand that's a number equal to a number. But when I don't specify it being 13, it now opens the door for that to be 13 or 14 or 15 or 13.1 or 13.01 or 13.0001. Okay, it can be anything. Does that make sense? Okay? And if I can somehow kind of sift and stitch all this stuff together and come out with the conclusion at the end that AEC is equal to DEB, I've proven then that that process would work regardless of what I chose for my values of 1 and 3, or measure of 1 and measure of 3. Okay, so that's given. The second statement here, they say angle 2 is equal to angle 2. What did we say yesterday? If we write a statement like this where the left-hand side is identical to the right-hand side, remember what that property was? Reflexive. Okay? And guys, right now, the reason that we're going to usually do that, the reason we're going to usually use the reflexive property is because the next thing we want to do is add it to something. We want to add it to both sides of an equation. So basically we're telling people, even though I don't know what the number is behind that symbol, I'm going to tell you that's the same number as what's behind that symbol. Does that make sense? Okay? So then, if we look at that statement right there, the statement 3 look a lot like it. What I've highlighted is the same, right? But what did we do to statement number 1 to generate statement number 3? You added something to both sides, right? But that thing we added to both sides, and statement number 2 we said was the same amount, right? So remember yesterday, if I start with 2 things that are equal, and I add a third thing to both sides, isn't that the addition property of equality that allows me to do that? Okay. And now this next step, this step 4 here, the statement 4, would align itself with step 5 on that handout that I gave you, where you have to look at your picture. You have to look at your picture, and we look at angles, and if we got angles in our picture, chances are we want to use angle addition. So I want to look at those 2 angles right there. Would you agree that 1 plus 2 is that statement right there? If I look at 1 plus 2, does that give me A to E to C? Okay. The next one, I'm going to look at 2 and 3. Would you agree that 2 plus 3, looking at my picture, does give me angle DEB? Okay, are we adding angles there? Okay, and if I'm adding angles to get a third, that's angle addition. Postulate. Okay. Now, here's the hard part. Step 6 and 7. It's using the law of detachment, law of syllogism. It's taking things that we've already stated. Steps 1, 2, 3, and 4. And you're going to pick out some of those and stitch them together to come up with something that's completely new, but is a fact. And here's the thing. Do you have, let's say that the statement 3 and 5 are going to actually be the same thing. Okay? I want to rewrite statement 3, but instead of calling it 1 plus 2, okay, instead of calling the left-hand side 1 plus 2, in statement 4, what have I called 1? What have I said that 1 plus 2 is also equal to? You see here how 1 plus 2 we said is equal to AEC? So can't I take what I've got in this block here and rewrite it as AEC? Does that make sense? And then on this side I got 3 plus 2. Well, didn't we say 3 plus 2 was also the same thing as DEB? So I take those things in those blocks and I replace them with what they're equal to. What's replacing something with what it's equal to? Substitution. Okay. And now we get to a point where our last statement matches with what our approved statement was, so that tells us we're done. Okay. Now, guys, I understand. I'm 100% with you. Okay. It's hard to work in a room that's 94 degrees. Okay. It's even harder to work on something that maybe you don't see the purpose of right away, and maybe is not, watching Netflix, right? Okay, it's not that fun, correct? Okay? But you will be held accountable for it, all right? So, like dozing off, putting heads down, not following along, that's going to come back to bite you in the butt. Okay, so, and I know the conditions they're not aligned with us to be successful right now. Maybe at the end of the week it will cool down a little bit. You got to fight through that stuff, okay? There'll be points in your life where you've got to fight adversity. This is an adverse situation, okay? There is a new homework assignment. It's not due tomorrow, okay? I think I got it due Thursday, okay? But you can start it tonight.